In our last video, we talked about the first law of thermodynamics for a constant volume, for a control volume. Now we're going to get into the first law of thermodynamics for a steady state process. So the difference is, between these two is with a control mass, let's just say we had a piston and we put a little bit of H2O in there and we add heat to it, so there's some heat in. Well, some of that will turn into, still be some water, but there'll also be some gas in there. So, H2O liquid and H2O gas. So in this situation, which we've been using a lot, there's only this water. That's all there is. In a steady state process, there's going to be a perpetual input of water. Let me show you. So let's say we have a feed line of liquid H2O, so H2O in its liquid phase, and I put it through a device called a boiler. Now what a boiler does is it boils water. So let's make that be a little, not much better, but so liquid water comes in and steam comes out, and that's all it is. So let's say so in this, back with a control mass, we have mass. We work with a mass. Now that's to say we're working with 1 kilogram. In this situation, we have a mass flow rate, which is kilograms per second. Sorry, this marker's not working too well. So let's say we have like 1 kilogram per second, which means every second 1 kilogram is coming in and 1 kilogram is coming out of water. Now, mass in has to equal mass out. That's just because if mass in was greater than mass out, there'd just be so much water in this boiler that it would explode, and if mass out was greater than mass in, well, eventually we'll run out of water in this device, and then eventually it'll just come back down to mass in equals mass out. So there's only one mass flow rate. So in this situation, we have a control mass. In this situation, we have a control volume, which instead of looking at one hunk of mass, we're looking at one area, one volume. In this case, the boiler. We denote a control volume by this little dashed line around it. So when we deal with a control volume, we're just looking at this one situation. So in the boiler, there's water turning into gas at a constant rate, at a steady rate. So before, in control mass, we had, when dealing with the first law, we had Q minus W equals the change in internal energy. We still have that. It's not going to look like it at first, but it really is pretty much the same equation, just taking into consideration time. So to take the first law and apply it to this situation, we have Q with respect with time, that's what this dot means, plus the mass flow rate in times enthalpy in plus velocity in squared over 2 plus the gravitational constant 9.81 meters per second squared times the height, but since we're already using h, I'm just going to use the letter z in, equals work with respect to time, or power, because kilojoules per second is a unit of power, but we can just say that's the same thing as work with respect with time, what this dot takes care of, plus mass flow rate out, times enthalpy out plus velocity out squared over 2 plus gz out. So what does this equation mean? Well, we have the Q and W with respect to time, just like we have in the original equation. So what this is really just a comparison of energies. Mass times enthalpy is energy, that's heat. Mass times velocity squared over 2, that's the formula for kinetic energy that we did all the way back in physics. And mass times height times the gravitational constant is the formula for potential energy. So we can rewrite this equation as Q dot minus W dot equals the mass flow rate, because mass without in or out, because they equal each other, so we can just condense it as one variable, times delta H plus delta V squared over 2 plus delta ZG, which is pretty similar to, which is analogous to the U2 minus U1, which is just M times delta U that we were doing before. So these equations really aren't too different from one another, this one and this one. It's just there's a couple more numbers we're going to have to incorporate into the equation, which really isn't that big of a deal. So that's pretty much what first law for a steady state process is. The next few videos we're going to be dealing with different devices. The boiler is just one of many different devices. We can work with turbines and compressors and heat exchangers. Each has its own assumptions that involve this equation. Like for instance in the boiler, there was no work being done. There was nothing turning, nothing moving, so work wasn't being done. And the height, let's just say they came in at the same height or even roughly the same height, we don't have to worry about this. And when you do it out a few times, when you do a few of the problems out, you'll see that the changes in kinetic and changes in potential energy are really minuscule compared to the change in enthalpy and heat energy, because that is the biggest, by far, the amount of energy that changes. And a lot of times we just assume we don't even take these into consideration because the changes are just so small that it's it's extra work that you don't need to do when the answer comes out to be pretty much the same answer, give or take very small percentages in difference. So yeah, in the next few we're going to be dealing with next few videos are going to be dealing with turbines, other heat exchangers, and so on and so forth. So good luck.